Okay, let's unpack this. We are embarking on a really high-stakes deep dive today. We're moving past the usual consumer tech talk. We're diving deep into the highly specialized, sometimes pretty unforgiving world of industrial process automation.
That's right. This is where the rubber meets the road,
Hmm.
industrially speaking. Think about it. These precision sensors, they're like the nervous system for our entire infrastructure.
Exactly, making sure the power stays on, chemicals get mixed safely, the food we eat is, produced with absolute accuracy. It's critical stuff.
And today we're really zooming in on the foundational measurement tech.
Hmm.
So flow, level, pressure, and also those advanced analytical instruments. The sources we've looked at, they give a fantastic map, not just of the science behind these sensors, which is fascinating in itself,
Right.
but also the critical real-world market dynamics that actually drive which sensor gets picked. We're looking particularly at how these choices play out in, say, rapidly developing industrial areas.
Yeah, and that regional snapshot you mentioned, like in Bangladesh, for example, with
Yeah.
all those diverse sectors, metal, paper, cement, power, food and bev, textiles, it's huge. What really jumps out is that it's not just about who's cheapest.
Oh, definitely not. It's way more complex. In these kinds of environments, reliability, that's the real currency. The big challenge is building that long-term customer confidence. You obviously need top-notch technical gear, but just as important, maybe even more so, is the whole package responsiveness, having local expertise on the ground, solid after-sales service.
Because downtime is killer.
Exactly. When a key measurement point fails, even minutes can mean thousands, tens of thousands of dollars lost, damaged product, lost production. So the selling approach, it has to be relationship-based. It's engineering solutions, not just shifting boxes.
That really sets up this interesting contrast you see in the competitive landscape, which our sources lay out really clearly. It's the broad generalist versus the super focused specialist.
Mhm.
On one side, you've got a giant ABB, huge portfolio, right? Automation systems, electrical products, a massive range of instruments. They can basically outfit the entire factory.
They offer the whole ecosystem, yeah. And then on the other side, you have someone like Andrus plus Hauser, E plus H. They're the specialists. Their whole game is measurement excellence, period.
Yeah. So how do they differentiate specifically?
Well, they push hard on extreme accuracy. They develop instruments that are really tailored for tough, compliance-heavy industries. Think food and beverage, pharmaceuticals, high-purity chemicals, and crucially, they invest a lot in advanced IoT stuff, Industrial Internet of Things.
Meaning the instruments are smarter.
Exactly.
Yeah.
They're not just measuring. They're actively diagnosing their own health.
Hmm.
They're feeding predictive maintenance data back to the control room. So E plus H isn't just selling a sensor. They're selling trust, really. Trust powered by diagnostic data.
Okay, so that brings us to our mission today. We want to equip you, the listener, with the kind of mental toolkit a seasoned consultative engineer would have.
Hmm.
The goal is when you hear about a challenging application, maybe measuring hot, abrasive slurry flow, something nasty like that,
Yeah, the tough ones.
you can immediately grasp the fundamental technical trade-offs involved in picking the right instrument. We're going beyond just product names here. We're getting into the physics of selection.
Understanding the why behind the choice. That's the key.
Okay, here's where it gets really interesting. Before we even start debating, vortex versus Coriolis or radar versus ultrasonic, we need to nail down the core philosophy. How do you even approach specifying an instrument?
It really is a philosophy. It's a disciplined approach.
Yeah?
You absolutely cannot walk in with a favorite technology already in mind. That's a recipe for disaster.
Right, you have to be objective.
Totally. The product selection is governed by a pretty strict hierarchy. First, ensure accuracy, then reliability, after that safety, and finally compliance. And all of this is based on matching the sensor's physical capabilities to the actual process environment. If you mess this up,
The consequences can be huge.
massive, inaccurate batches, sure,
Yeah.
but also potential regulatory fines, safety incidents, even, explosions and worst-case scenarios. It's serious.
Our sources gave us something really valuable here, though, a kind of shortcut or maybe a structured approach, the customer questioning framework.
Ah, yes, the 7 steps. It's brilliant because if you follow it rigorously, it almost forces the right instrument choice. It guides you there.
Let's break them down. What's step one?
Step 1 is the absolute basic, measurement objective. What are you trying to measure? Flow, level,
Hmm.
pressure, temperature. Or is it something analytical, like pH or conductivity? Sounds simple, but you got to start there.
Okay, easy enough. Step two.
Step 2, process details. Now it gets technical. First hurdle. What's the fluid phase? Is it a liquid, a gas, maybe a slurry, or steam? Then, what are its intrinsic properties? Viscosity, density. And absolutely critical for flow measurement. What's its conductivity?
Okay. That conductivity question,
Yeah.
that's the big one for mag meters, right? It's like the first sorting mechanism.
Exactly. If you're dealing with something like high-purity oil or hydrocarbon gas, boom, you've just eliminated a huge category of flow meters right off the bat. Mag meters are out.
Okay, makes sense. What's step 3?
Step 3 covers operating conditions, temperature and pressure. What are the maximums? What are the minimums? Does it cycle? And, importantly, is the medium aggressive? Is it corrosive? If your process regularly hits, say, 150 degrees Celsius,
You need special gear.
you absolutely do. You're looking at specialized remote seals, specific fill fluids for those seals. Otherwise, the transmitter electronics are just going to cook.
Yeah.
Same for pressure. If you get spikes, that transmitter needs high overpressure capability or it's toast.
Right. Then we get to the physical installation itself. Step 4.
Step 4, insulation details. Pipe size, obviously. Pipe material matters too. What about the tank? Is it tall and narrow, short and wide? Does it have internal structures? And crucially, are there space constraints? This bites people all the time.
How so?
Well, remember, lots of flow technologies, especially the older ones like Vortex or DP flowmeters, need long, straight, undisturbed pipe runs upstream and downstream.
To get a smooth flow profile.
Exactly. If you're trying to cram instruments onto a crowded skid unit, you might simply not have that space. You might be forced into using a more expensive but more compact technology, like Coriolis, purely because of the installation real estate available.
Interesting constraint. Okay, step 5. What about the area around the instrument?
Step 5, environmental and safety. This defines the instrument's housing, its certifications. Is it going into a hazardous area? Does it need intrinsic safety certs like ATEX or ISEX?
Flammable gases or dusts?
Right. Or, for level, does the tank have tons of foam on top, heavy vapor? Lots of agitation that might confuse the sensor. Is there high vibration from nearby pumps or machinery? That's especially critical for vibration-sensitive tech like Coriolis meters.
Okay, makes sense. Step 6 sounds important. Accuracy and compliance. This is where the money talk starts, maybe?
Often, yes. Step 6, accuracy and compliance. This is where you define how good the measurement needs to be. Are we talking standard process control, maybe controlling a valve where, plus or minus 1% error is perfectly fine?
Yeah.
Or is this high-stakes custody transfer, where you're literally buying or selling the material based on that meter reading?
Like oil and gas pipelines or loading chemicals onto a truck.
Precisely. Custody transfer demands ultra-high accuracy. We're talking maybe plus or minus 0.1%, sometimes even better. And then what regulations apply? FDA for food and pharma. Specific hygienic standards like 3A. Industry-specific certifications. These dictate everything: materials of construction, the types of process connections allowed, even the type of oil inside a diaphragm seal.
Wow, okay. Lots to consider there. And finally, the practical side. Step 7.
Step 7, budget and maintenance. The dollars and cents, but not just up front. It's the initial capital cost versus the total cost of ownership.
Ah, the long game.
Exactly. A differential pressure meter using orifice plates might be really cheap to buy initially, but if those impulse lines get clogged every week with sludge and you need specialized maintenance folks to come out and clean them constantly,
That adds up fast.
that operational cost can absolutely dwarf the initial savings. So you have to consider the plant's maintenance philosophy. Do they prefer higher tech, maybe zero maintenance devices? Or are they comfortable with lower tech, higher touch solutions that need regular attention?
So following those 7 steps.
If you rigorously go through those 7 questions, you've basically defined all the critical parameters. Technical mutability, safety, compliance, commercial reality, they all get aligned before you even think about getting a quote. It forces a holistic view.
Okay, let's apply that framework. Let's dive into the first big category, flow measurement. Measuring how much stuff is moving through a pipe. And the choice here, as you said, really depends on the fluid's personality, right? Is it conductive, hot, viscous, dirty, clean?
Precisely. And if we start at the top, the benchmark, the one everyone compares against, that's the Coriolis flowmeter.
The gold standard, you called it earlier.
It really is. It uses the Coriolis effect, a physical principle acting on vibrating tubes inside the meter to measure mass flow directly.
Why is measuring mass directly such a big deal?
Because most other flow meters measure volume. Think liters per minute or gallons per minute. But the volume of a fluid, especially a gas or even some liquids, changes with temperature and pressure. Its density changes.
Ah, so a volumetric reading might not represent the actual amount of stuff.
Exactly. A Coriolis meter measures kilograms per hour or pounds per minute, mass. And that measurement is fundamentally unaffected by changes in the fluid's density, its viscosity, or its temperature. It just measures the mass passing through.
Plus, it gives you more than just flow.
Yeah, that's the other big advantage. It's typically a multivariable device.
Yeah.
So you get mass flow, and you usually get density, and you get temperature, all from the one instrument.
Okay, so that makes it ideal for.
Critical custody transfer, like we mentioned, high accuracy blending operations, precise chemical dosing, anywhere you need top-tier accuracy, often down to plus or minus 0.1%. It's unmatched for that.
But it's not perfect. You mentioned trade-offs. Cost is one, I assume.
Cost is definitely a major factor, yes. They are significantly more expensive than most other flow technologies. But it's not just cost.
What else? Installation. You mentioned they get heavy.
They do, especially for larger pipe sizes. Installing a very large Coriolis meter can be a serious mechanical challenge. They can weigh hundreds, even thousands of pounds. And remember, step 5 from our framework, environment.
Vibration sensitive.
Bingo. Coriolis meters are essentially very sophisticated, very sensitive vibrating systems, like tuning forks. If you mount one right next to a big, heavy piece of vibrating machinery like a large pump or a compressor, without using really rigid supports and proper installation techniques,
It messes up the reading.
it introduces noise and error
Right.
into that high accuracy measurement. You can compromise that high at 0.1% accuracy very easily with a poor installation.
Okay, so Coriolis is the high accuracy, high cost, somewhat sensitive option. Let's pivot to the workhorse for conductive fluids, the electromagnetic flow meter. The mag meter. I always thought the principle here was quite elegant. No moving parts, right? Great for dirty water.
Absolutely. It's the undisputed king of water, wastewater, slurries, pulp stock, and paper mills, basically anything that conducts electricity, even slightly. It works on Faraday's law of induction. You create a magnetic field across the pipe, the conductive liquid flows through it, and that moving conductor generates a tiny voltage. The faster the flow, the higher the voltage. Simple as that.
And the lack of moving parts is key for reliability.
Huge. No bearings to wear out, no rotors to get jammed by debris or corroded by chemicals. It makes them incredibly robust and virtually maintenance-free while still offering pretty high accuracy, typically around 0.2%. That's why they dominate in water treatment, mining, food processing with conductive liquids.
But the huge limitation is right there in the name. Electromagnetic needs conductivity.
That's the Achilles heel. If your fluid is non-conductive, think oils, hydrocarbons, solvents, very pure deionized water with conductivity below, say, 5 microsiemens per centimeter. The magnet simply won't work. No conductive fluid, no induced voltage, dead in the water.
And installation pitfalls. You mentioned grounding.
Critically important. For the meter to measure that tiny induced voltage accurately, the fluid and the meter body need to be properly grounded to the surrounding pipework. If you have poor grounding, you pick up stray electrical noise from pumps, motors, VFDs.
And it swamps the signal.
Completely. You get erratic, unstable readings. Also, you absolutely must ensure the pipe is always full of liquid. Especially in vertical runs, you need upward flow to guarantee a full pipe. And like many meters, they need some straight pipe runs, maybe 5 pipe diameters upstream, 3 downstream, to get a reasonably stable flow profile for accurate measurement.
Okay, mag meters for conductive liquids. What about steam or high-pressure gases? You mentioned a specialist.
Ah, yes, the Vortex Flowmeter, often called the steam specialist. And for good reason. It's a very robust technology, great for measuring steam flow, but also works well for high-pressure gases and even some high-temperature liquids. The principle is neat. You place a specifically shaped bar, called a bluff body, directly into the flow stream. As the fluid flows past it, it creates these little swirls or vortices that shed off alternating sides of the bar.
Like ripples behind a rock in a stream.
Exactly like that. And the frequency at which these vortices shed is directly proportional to the flow velocity. Count the vortices, you know the flow rate.
Simple, robust. Sounds good for utilities, like measuring steam consumption for cleaning processes, CIP or SIP you mentioned.
Perfect for that. Compressed airlines too. But there's a big but with installation.
Let me guess. Straight pipe runs.
Lots of them. The Vortex meter is extremely sensitive to disturbances in the flow profile. If the flow hitting that bluff body is swirling or turbulent, the vortex shedding becomes chaotic and unstable. The measurement just falls apart.
So you need really smooth flow.
You need a fully developed, stable flow profile. That means you often need significant straight pipe runs. We're talking maybe 10 pipe diameters upstream of the meter and maybe 5 diameters downstream.
That's a lot of pipe.
It can be a major constraint in tight installations. And they're also sensitive to pulsation if you have a pump causing pressure pulses that can also disrupt the vortex shedding and mess up the reading.
Okay, vortex for steam and gas, but needs space. Now, the fourth type, the real old guard, differential pressure, DP flow meters, these seem to be everywhere, but you hinted they're high maintenance.
They were ubiquitous, largely due to historical reasons and standardization. The DP meter is the utility player, the jack of all trades. It doesn't measure flow directly. It works by creating a deliberate restriction in the pipe, usually an orifice plate, a simple metal disc with a hole, but sometimes a more complex Venturi tube or flow nozzle. Then it measures the pressure before the restriction and the pressure after the restriction. The difference in pressure, the dP, is related to the flow rate by Bernoulli's principle. Higher flow means a bigger pressure drop.
Sounds simple enough. Cheap up front, too, right?
Usually the cheapest initial cost for the primary element, yeah. But the accuracy is generally lower, maybe 91% is typical, sometimes worse depending on the setup, and the real cost comes later.
The maintenance headache, those impulse lines.
Exactly. You have these small tubes, the impulse lines, running from the pressure taps on either side of the orifice plate back to the DP transmitter, which might be located some distance away. In steam applications, these lines fill up with condensate. In dirty liquid or slurry applications, they get clogged with sludge, solids, debris.
Which gives a false reading.
Completely false. If one line gets partially blocked, the DP reading changes, and the transmitter thinks the flow is changed, even if it hasn't. I've seen entire batches of product ruined because clogged impulse lines led to incorrect ingredient additions. They need constant checking, flushing, maintenance.
Plus, that restriction causes a permanent energy loss.
Yeah, absolutely. Squeezing the flow through that orifice plate creates a pressure drop that never recovers. That means your pumps have to work harder, continuously, wasting energy 24/7 just to push the fluid past the meter. It's an ongoing operational cost. And yes, they also require very long, straight pipe runs, sometimes up to 20 pipe diameters upstream, to get decent accuracy.
Okay, DP, cheap upfront, potentially high maintenance, energy hog, needs lots of space. One more flow type, the thermal mass flow meter. You called it the gas utility watchdog.
Right, this one's specifically for gases. It uses a completely different principle, heat transfer. Typically, it has two temperature sensors in the flow stream. One measures the gas temperature, and the other is heated to maintain a constant temperature difference above the gas temp. As the gas flows past, it cools the heated sensor.
And the more gas flows, the more cooling effect.
Exactly. The amount of electrical power needed to maintain that constant temperature difference is directly proportional to the mass flow rate of the gas. More mass flow carries away more heat.
Ah, direct mass flow for gases. That sounds useful. No need for separate pressure and temperature sensors to calculate density.
Correct. That's the big advantage for gas measurement. It gives you direct mass flow, like in standard cubic feet per minute or kilograms per hour, without needing external pressure and temperature compensation. This makes it excellent for monitoring utility gases like compressed air, nitrogen, CO2. Great for tracking consumption, finding leaks, or measuring low flow rates accurately.
But strictly gases, right?
Absolutely. Do not try to use a thermal mass flow meter on liquids or steam. It won't work, and you'll likely damage it. And one other key point. They need to be calibrated for the specific gas or gas mixture being measured. Different gases have different thermal properties. If you calibrate it for air and then try to measure pure nitrogen or CO2, the reading will be wrong unless you recalibrate or apply a correction factor.
Okay, we've covered things moving through pipes. Let's switch gears to things sitting in tanks, level measurement. Here, the challenge isn't so much the flow profile, but fighting against all the physical chaos that can happen inside a storage tank, right?
Exactly. The choice of level technology is almost entirely dictated by the presence of interference. You have to ask, is the tank pressurized? Is the liquid boiling, creating heavy vapor? Is there foam sitting on the surface? Is it a dusty solid in a silo? Is the surface turbulent?
And if the answer to any of those is yes, you probably
head straight for radar-level transmitters.
radar. Uses microwaves. And the big advantage seems to be that microwaves just don't care much about that chaos.
Largely, yes. They are incredibly reliable in harsh conditions. Microwaves generally cut straight through processed vapors. They aren't really affected by temperature changes in the headspace. And they can often see through foam or dust layers that would completely confuse other technologies.
So they're essential for tough applications.
Definitely. Measuring solids like cement powder or plastic pellets in a tall silo. Radar. Measuring challenging liquids like hot fuming black liquor in a paper mill recovery boiler. Radar. It provides reliable, continuous measurement where other things fail. Plus, you have non-contact options, which is great for hygiene or very corrosive liquids.
And within radar, there are two main types, based on how the signal travels. Free space versus guided wave.
Correct. Free space radar, sometimes called non-contact radar, beams the microwaves down from the top of the tank towards the surface and measures the reflection time. It's simple, non-intrusive. But guided wave radar, GWR, is often the real problem solver for tricky applications. Here, the microwave pulses are sent down a rigid probe or a flexible cable that extends into the liquid.
So you're guiding the signal path. What's the advantage of that?
By guiding the signal, GWR concentrates the microwave energy. This makes it far more effective in several situations. First, for high accuracy, especially in narrow tanks or tanks with lots of internal obstructions like pipes or agitator blades where a free space signal might scatter. Second, when the liquid has a very low dielectric constant.
Meaning it doesn't reflect microwaves well?
Exactly. Some hydrocarbons or solvents are poor reflectors. GWR focuses the energy, so you get a much stronger return signal, even from low dielectric liquids.
And you mentioned interface measurement earlier. GWR is key for that.
It's the standard, yes. If you have two immiscible liquids layered in a tank, like oil floating on water, GWR is the best way to measure not just the overall level, but also the precise height of the interface between the two liquids.
How does it do that?
Because the microwave signal travels at different speeds through the two different liquids, due to their different dielectric constants. When the pulse hits the interface layer, part of the signal reflects back and part continues down, reflecting off the bottom layer or the tank bottom. By analyzing these multiple reflections, the transmitter can accurately track both the top level and the interface level.
And GWR handles foam and turbulence better too.
Much better than free space radar. Because the signal is constrained to the probe or cable, it's less likely to be scattered or absorbed by surface foam or heavy turbulence. It just powers right through it.
Okay, so radar, especially GWR, is the robust choice for tough conditions. What's the cheaper, simpler alternative that struggles with that stuff?
That would be ultrasonic level transmitters.
Uses sound waves instead of microwaves.
Right. Sends a pulse of high-frequency sound down, bounces off the liquid surface, measures the time it takes to return. Simple, often cost-effective. Works perfectly well for straightforward applications, measuring water level in an open sump, clean liquids in a basic storage tank. Non-contact, which is nice.
But the big limitation is sound waves are easily disrupted.
That's the major drawback. Unlike microwaves, sound waves are readily absorbed or scattered by things like heavy foam on the liquid surface, dense process vapors, significant dust in the headspace, or even strong temperature gradients that can bend the sound path.
So if you have a tank where a chemical reaction is causing lots of vapor or foam,
Forget ultrasonic. The signal just gets lost. You'll get erratic readings or no reading at all. If you need reliability in a challenging environment, especially one with vapor or foam, you really have to step up to radar. Ultrasonic is best for clean, calm, open applications.
okay. Moving on from continuous level measurement, what about just knowing if the level is high or low, like for alarms or pump control?
For simple point level detection, high alarm, low alarm, preventing overfills or dry runs, you often use simpler switch technologies. Two common ones are capacitance and vibrating fork switches.
Capacitance first, how does that work?
A capacitance probe acts like one plate of a capacitor, and the metal tank wall, or a reference probe, acts as the other plate. The material between them, air or the liquid, is the dielectric. As the liquid level rises and covers the probe, the overall capacitance changes because the liquid has a different dielectric constant than air.
Sounds clever, but I've heard they can be finicky.
They can be. The big issue is sensitivity to coating or buildup on the probe. If sticky material coats the sensor, it changes the capacitance reading, giving a false level indication. They also get tripped up if the dielectric constant of the liquid itself changes significantly, maybe due to temperature or composition changes. So best for clean, simple liquids with stable properties, requires more maintenance attention.
Okay, so what's the more robust option for just a simple switch point? The vibrating fork, like the Liquifont you mentioned.
Ah, the vibrating fork, yes. Like the Indris, plus Hauser Liquifant, or similar devices like the ABB LVS200. These are incredibly simple and reliable point-level switches. They have two small metal tines, like a tuning fork, which are kept vibrating at their natural frequency by piezoelectric crystals. When the liquid level reaches the fork and covers the tines,
It dampens the vibration.
exactly. The liquid dampens the vibration, the electronics detect that change, and the switch trips signaling a high level or a low level.
And the advantage is robustness.
Immense robustness. They are virtually immune to things that plague other technologies. Foam, bubbles, turbulence, minor coating, changing liquid properties like density or dielectric constant. The vibrating fork generally doesn't care. It just detects the presence or absence of liquid reliably.
So perfect for safety interlocks.
Absolutely. Their primary role is often in safety systems. High-level alarm to prevent tank overflow, low-level alarm to shut down a pump before it runs dry and destroys itself. Simple, effective, reliable safety switches.
Okay, one last level principle, and it brings us back to pressure measurement, hydrostatic level.
Right. This isn't a direct level measurement technology itself, but rather an application of pressure measurement. You place a pressure transmitter at the bottom of the tank, or connected via tube. It measures the pressure exerted by the column of liquid above it. Since we know pressure equals height times density times gravity, P-A-H-A-G, if we know the density of the liquid and gravity, G, is constant.
You can calculate the height, H, which is the level.
Precisely. You use either a gauge pressure transmitter for an open vented tank or a differential pressure DP transmitter for a closed or pressurized tank. For a DP setup, one side measures the hydrostatic head at the bottom, and the other side measures the gas pressure in the headspace, effectively subtracting the gas pressure to get just the liquid head pressure.
Seems straightforward. What's the crucial sensitivity here? You mentioned density.
Density is everything for hydrostatic level accuracy. The calculation relies entirely on knowing the specific gravity or density of the liquid accurately. If the temperature of the liquid changes significantly, its density will change. If the composition of the liquid changes, its density might change.
And if the density changes, but the pressure transmitter doesn't know?
The pressure reading itself will still be correct. It's accurately measuring the pressure. But the level calculated from that pressure using the old density value will instantly become inaccurate. So hydrostatic level is great for stable liquids where density is constant or where density changes can be compensated for, maybe with a separate temperature measurement. But if density fluctuates wildly and unpredictably, hydrostatic level measurement will be unreliable.
All right, we've mentioned pressure quite a bit. Let's dive specifically into pressure measurement itself. This seems like where the engineering details and the specs really matter. We should probably start with the fundamental references. Pressure is always measured relative to something, right?
That's the key concept. You have three main types. First, gauge pressure. This is probably the most common. Think of the ABB 261G model. It measures pressure relative to the current local atmospheric pressure. So zero on a gauge pressure transmitter means it's sensing the same pressure as the air around it.
And this is used for?
Standard process line monitoring. Measuring pressure in pipes, reactors, basic tank pressure. It ignores changes in atmospheric pressure because both the process and the reference side of the sensor see those changes. Second, absolute pressure. Like the ABB 261A. This measures pressure relative to a perfect vacuum. Zero absolute pressure is the complete absence of any pressure. The reference side of the sensor is sealed with a hard vacuum inside.
Why would you need that?
It's essential for applications where atmospheric pressure changes would affect the process or the measurement itself. Think vacuum applications monitoring vacuum distillation columns, evaporators, vacuum packaging machines. If you use a gauge sensor there, changes in the weather, barometric pressure, would look like changes in your vacuum level. Absolute pressure gives a true reading independent of atmospheric conditions.
Okay, gauge versus absolute. And the third type we've already touched on, differential pressure, DP.
Right. DP measures simply the difference between two pressure points. We talked about its use for flow measurement with orifice plates and for hydrostatic level in pressurized tanks. But it has other uses too, like monitoring filter performance. You measure the pressure before a filter and the pressure after it as the filter gets clogged.
The pressure drop across it increases, the DP goes up.
Exactly. It's a great indicator that the filter needs cleaning or changing. But again, we have to hammer on the potential error source for DP systems.
Those impulse lines again.
Those darn impulse lines. If they get blocked, if they leak, if condensate builds up unevenly in them, it creates a false differential pressure reading. The transmitter sees a DP change, but it's not real. It's just an artifact of the plumbing. Maintenance is key for reliable DP measurement.
Now, protecting the actual sensor inside the transmitter from nasty process stuff, heat, corrosion, gunk, that's where diaphragm seals come in.
They are absolutely essential for instrument longevity and reliability in tough processes. A diaphragm seal basically creates a barrier. It has a flexible metal diaphragm that contacts the process fluid. Behind that diaphragm is a small chamber and capillary tube completely filled with a special incompressible oil. This oil transmits the process pressure hydraulically back to the actual pressure sensor, which stays safe and sound inside the transmitter housing, away from the harsh stuff.
So the sensor only ever sees clean fill oil.
Precisely. This allows you to measure pressure in extremely hot processes, highly corrosive chemicals, or very viscous fluids or slurries that would instantly clog a standard transmitter's pressure port. Think about measuring black liquor pressure in a paper mill. It's hot, corrosive, and tends to solidify. You need diaphragm seals with the right materials and fill fluid for that.
Okay, let's get into the specifics. Using that ABB 2600T series, the 261G for gauge, 261A for absolute as an example, the specs mention a base accuracy of 0.1%.
That's pretty good. It's very good for a standard process transmitter. But the real lesson in those specs isn't just the base accuracy, it's how you maintain that accuracy in practice. And that brings us to the concept of turn-down ratio.
Turn down. Explain that. What does it mean?
Okay, every pressure sensor has a maximum pressure it's designed to measure accurately. That's its upper range limit, or URL. Let's say a sensor has a URL of 100 psi. But maybe your actual process only operates between, say, 0 and 10 psi. You would configure the transmitter to output 4 mA at 0 psi and 20 mA at 10 psi. That 10 psi range you're using is called the span. The turn-down ratio, TD, is simply the URL divided by the span you've set. In this case, 100 psi URL divided by 10 psi span gives you a turn-down of 10.1.
Okay, so it's a measure of how much of the sensor's full capability you're actually using?
Exactly. And the 2600T series, like many modern transmitters, offers high flexibility. They advertise turndowns of up to 20.1, sometimes more. This means you could potentially use that 100 psi sensor to measure a span as small as 5 psi. 105 equals 20.1.
Sounds convenient. Fewer sensor models needed in inventory, maybe.
It is convenient for inventory, absolutely. But here's the crucial insight for performance. Using a very high turn-down ratio slightly degrades the accuracy.
Why is that?
Think about it. The sensor is physically built and tested to perform best over its full calibrated range, or close to it. When you turn it down dramatically, say 20.1, you're asking the electronics to accurately measure and amplify a very, very small change in the sensor's output signal relative to its full capacity.
So you're amplifying noise along with the signal.
Essentially, yes. Small nonlinearities or noise that are negligible over the full range become more significant when you zoom in on a tiny portion of it.
Right.
Our sources even quantify this. For the 2600T, if your turn down is greater than 10.1, you have to add an additional error factor. The formula is 1.005 times the turn down minus 0.05% applied to your set span.
Okay, let's make that concrete. If I use a 20.1 turn down.
Okay, plug 20 into the formula.
Okay.
0.005, 2005, 0.1, 0.05, 0.055. So you add an extra 0.05% error to your span on top of the base accuracy just because you used a high turn down.
Ah, so the lesson is, always try to pick a sensor model where the URL is as close as possible to your required operating span. Use the lowest possible turn down.
Precisely. If you need to measure 0.50 psi, don't use a 0.500 psi sensor range down 10.1. If there's a 0.100 psi sensor available that you could use at only 2.1 turn down. Choosing the sensor with the lowest URL that covers your range will always give you the best possible accuracy because you minimize the turn down effect. You're literally buying less error by selecting the right range code.
That's a really important practical point. Okay, beyond accuracy, let's talk about surviving the process. Temperature is a big one. You mentioned those fill fluids and the diaphragm seals.
Yes, if the process temperature gets too high for the transmitter electronics, which are usually rated to maybe 85 degrees C or 120 degrees depending on the model, the diaphragm seal and its capillary tubing act as a heat barrier. The fill fluid inside becomes critical. The specs list different options. Silicone oil is common, handles fairly high temps. Fluorocarbon-based oils can go even higher, maybe up to 180 degrees C or more, and handle high pressure as well. But then there's white oil.
White oil specifically?
Food and pharma. Hygienic applications. If there's any chance that diaphragm could rupture and the fill fluid could leak into the product.
It has to be food safe.
Absolutely. White oil is typically FDA approved, non-toxic. Using anything else in a food, beverage, or pharmaceutical application is a major compliance violation. So for those industries, you'll see specifications not just for white oil fill, but also for hygienic process connections, things like tri-clamp fittings, Varavent, or dairy thread connections instead of standard pipe threads. And often additional certifications like 3A sanitary standards are required.
Got it. Compliance dictates materials. Let's quickly touch on safety certifications mentioned, like SLL2 and temperature classes. What do those mean for the user?
SLL2 stands for Safety Integrity Level 2. It's part of functional safety standards, like IEC 61508-61511. A SLL2 rating means the transmitter has been independently assessed and certified as having a very high level of reliability and diagnostic coverage, making it suitable for use in safety-critical shutdown systems. It's designed to perform its safety function reliably when needed.
And the temperature class? T rating.
That relates to explosion protection for hazardous areas like ATEX or ISEX zones. The T rating T4, T5, T6, etc., specifies the maximum surface temperature the transmitter housing could possibly reach under fault conditions. This is critical to ensure the device itself cannot become hot enough to ignite any flammable gas or vapor present in the surrounding atmosphere. You have to choose a T-class suitable for the ignition temperature of the specific hazards in that area.
Okay. And finally, how do you actually configure these things and get the data out?
The standard output is still the good old 420 milliamp analog current signal. It's simple, robust, easy to wire. 4 mA typically represents the low end of your measurement range, low range value or LRV, and 20 mA represents the high end, upper range value or URV. But overlaid on that 420 mA signal is usually a digital communication protocol, most commonly HART, Highway Addressable Remote Transducer.
What does HART let you do?
HART allows a handheld communicator or the control system itself to talk digitally to the transmitter over the same two wires. You can read not just the primary pressure value, but also secondary variables like sensor temperature, diagnostic information, is the sensor healthy, and you can remotely configure everything, change the range, LRV, URV, damping, tag names, etc. Some models might also have an optional local LCD display for configuration right at the device.
Okay, we've built a solid foundation on flow, level, and pressure. Let's move into Section 5. Specialized measurement and control synthesis. This feels like it's more about ensuring quality, measuring the composition of the product, and then tying all this sensor data together.
Exactly. Analytical measurements are the gatekeepers of quality and compliance. Let's start with arguably the most common one, pH measurement. pH, the measure of acidity or alkalinity, is critical in countless processes. Water treatment relies on it for chemical dosing. Food and beverage uses it to control fermentation, ensure product stability. Paper manufacturing needs it for bleaching stages and effluent control.
And getting pH wrong?
Yeah.
What are the consequences?
Pretty severe. If your pH is too low, too acidic, you can cause massive corrosion damage to pipes, tanks, equipment. Very expensive. If it's too high, too alkaline, you might get scaling or deposits forming, reactions might not proceed correctly, or crucially for many plants, you might violate environmental regulations for your wastewater discharge.
What's the challenge with measuring pH reliably?
Maintenance. The pH sensor itself, the electrode, usually relies on a very delicate glass membrane. This glass ages over time, it gets attacked by chemicals, it can be broken by solids, it gets fouled or coated, and its performance drifts with temperature.
So they need constant babysitting.
They require frequent, regular calibration against known buffer solutions to remain accurate, and eventually, no matter how well you maintain them, the electrodes simply wear out and need replacement. Reliable pH measurement requires a commitment to ongoing maintenance.
Okay, pH is critical but needs care. What about conductivity measurement? You mentioned it briefly with magmeters, but here we're measuring it as a primary variable.
Right. Conductivity measures a solution's ability to conduct electricity, which is directly related to the concentration of dissolved ions, salts, acids, bases. It's essentially a measure of ionic purity.
So, used for checking water quality.
Very common application. Monitoring the purity of boiler feed water is critical. High conductivity means dissolved solids, which cause scale and corrosion in the boiler tubes. Big problems. It's also used extensively in food, beverage, and pharma for clean-in-place, CIP, or sterilize-in-place, SIP, validation. After cleaning equipment, you rinse with pure water and monitor the conductivity of the rinse water. When it drops back down to the level of pure water, you know the cleaning chemicals have been properly rinsed away.
Makes sense. Also for effluent monitoring.
Yes, ensuring discharged wastewater meets environmental limits for dissolved solids. Now, the sensor choice matters here, too. For relatively clean water, standard contacting sensors with 2 or 4 electrodes work fine.
But for dirty stuff.
If you're dealing with dirty wastewater, high concentrations, corrosive chemicals, or solutions that tend to coat sensors, you absolutely want to use toroidal conductivity sensors, also called inductive sensors.
Why are they better for those applications?
Because they work like 2 transformers. One coil induces a current in a loop of the processed liquid, and a second coil measures the magnitude of that induced current, which is proportional to the conductivity. Critically, the coils are typically encased in plastic, and there are no metal electrodes in direct contact with the process fluid.
So nothing to corrode or get coated.
Exactly. They are far less susceptible to fouling and corrosion in dirty or aggressive streams, much more reliable, much lower maintenance in those tough applications compared to contacting electrode sensors.
Okay. And briefly, 2 others mentioned. Dissolved oxygen, DO, and TOC. These sound environmentally focused.
They often are, but also have process uses. DO measures the amount of oxygen dissolved in a liquid, usually water. Its biggest application is in wastewater treatment. The biological treatment process relies on bacteria consuming waste, and those bacteria need oxygen to live.
So you measured DO to control the air blowers?
Precisely. You need to maintain a specific DO level enough for the good bacteria to thrive, but not too much, because running those massive air blowers is one of the biggest energy costs in a treatment plant. Optimizing DO control saves huge amounts of electricity. TOC, or total organic carbon, measures the amount of carbon bound in organic compounds in water. It's a general indicator of organic contamination, used for environmental monitoring of wastewater discharge, but also critically important for validating the purity of water used in pharmaceutical manufacturing. Water for injection, or WFI. You need extremely low TOC levels there.
Okay. Shifting from fluid properties to physical force.
Yeah.
The force and load measurement. Weighing things, basically.
Primarily, yes. The workhorse here is the load cell, which is typically based on strain gauge technology. You bond strain gauges to a precisely machined metal structure. When a weight or force is applied, the structure deforms slightly, stretching or compressing the strain gauges.
And that changes their electrical resistance.
Correct. That tiny change in resistance is measured and converted into a weight or force reading. Load cells are used everywhere. Under tanks or silos to measure inventory weight, think huge cement or grain silos, in batching systems for accurate ingredient weighing, on filling machines for controlling chemical dosing pumps based on weight. High-quality load cells can achieve incredible accuracy, sometimes down to dactyl 1%.
Now, you mentioned a specialized ABB sensor, the press ductor, uses a different principle, magnetoelasticity. Sounds exotic.
It is a bit specialized, but incredibly useful in certain industries. The press ductor technology leverages the magnetoelastic effect, the fact that the magnetic properties of some materials change when they are put under mechanical stress, tension or compression. It allows you to measure force or tension very accurately with no moving parts, and crucially, it's extremely resistant to overload damage. Very rugged.
Where would you use something like that?
Its main niche is web tension measurement. Think about machines making paper, plastic film, textiles, or metal strips. These materials, the web, are flying through the machine at high speed over rollers.
And you need to control how tightly they're pulled.
Absolutely critical. If the tension is too low, the web might wrinkle or wander off track. If it's too high, it could stretch or even break, causing costly downtime and waste. The press ductor sensors are built into the roller support bearings or mounted under rollers to provide a precise, real-time measurement of the web tension. This allows the control system to constantly adjust motor speeds or brakes to maintain the perfect tension, ensuring high product quality and maximizing production speed. It's vital for industries like paper and textiles.
Okay, so we have all this incredible data pouring in: flow rates, mass flow, density levels, interface levels, pressures, temperatures, pH, connectivity, DO, TOC, weights, tensions, coming from all these specialized sensors. The final piece is putting it all together, right? Making sense of it and controlling the process.
That's the crucial synthesis step. All these instruments are the eyes, ears, and nerve endings of the plant. That data typically flows back via 420 mA heart or field bus protocols to the plant's brain. This could be a PLC, programmable logic controller, like an ABB AC500, often used for controlling individual machines or smaller process units. Or, for larger, more complex plants, it feeds into a DCS, distributed control system, like ABB's System 800XA.
And the PLC or DCS uses that data to
execute the control strategy, to open and close valves, start and stop pumps, adjust heater power, manage sequences. It handles the centralized control, optimizes energy usage based on real-time measurements, and critically manages the safety interlocks we talked about, like shutting down that pump if the vibrating fork level switch signals a dry run condition, preventing damage.
And just having the data isn't always enough, especially for regulations. You need to record it securely.
Absolutely essential, particularly in regulated industries like pharma, FDA 21 CFR Part 11, or food, HACCP. You need secure, tamper-proof data recorders, like the NRIS plus Hauser Memograph M mentioned in the sources. These devices continuously log the critical process parameters, timestamp everything, and store it electronically, often with security features to prevent alteration. This creates the vital electronic audit trail needed to prove compliance to regulators, to troubleshoot process upsets after the fact, or to analyze historical data for process optimization projects. You can't manage what you don't measure, and you can't prove compliance or optimize effectively without reliable data logging. The whole system, from sensor physics to control logic to data archiving, is deeply interconnected.
So what does this all mean? We've covered a lot of ground, from basic principles to highly specialized tech. If we step back and try to synthesize this whole deep dive, the big takeaway seems clear. Mastering process instrumentation isn't really about memorizing hundreds of different product models.
Not at all. It's fundamentally about adopting that consultative engineering mindset. It's about knowing how to ask the right questions, those 7 key questions we discussed, to fully, deeply understand the process environment, the challenges, the potential interferences, and then crucially, it's about understanding, accepting, and intelligently managing the inherent technical trade-offs involved in every single instrument choice. There's rarely one perfect sensor for everything.
Yeah, those trade-offs were everywhere, weren't they? We saw it in Flow. Getting the absolute best accuracy meant choosing Coriolis, but accepting its high cost and demanding installation requirements.
Right. Or choosing a magmeter for its robustness in conductive slurries,
Yeah.
but knowing it's useless for oils.
In level measurement, achieving reliability in tanks with foam or vapor meant investing in radar, often guided wave radar, because the simpler, cheaper ultrasonic option would just fail under those conditions.
Exactly. Overcoming interference was key.
And in pressure, getting robust, reliable measurement in hot, corrosive processes depended entirely on selecting the right diaphragm seals, the correct materials, and even specific compliance-driven fill fluids like FDA-approved white oil for food applications. Ignoring those details leads to premature failure.
It's that ability to navigate the specifics, the subtleties, the trade-offs, based on a deep understanding of both the process and the measurement physics that really separates reliable, efficient, profitable operations from plants that are constantly fighting fires and dealing with instrument failures.
Which brings us to our final provocative thought for you, the listener, to chew on. We spent some time getting into the weeds on pressure transmitter specs, specifically how the accuracy of a high-precision device, like the ABB261GA, is actually influenced by how it's configured internally, specifically that turn-down ratio you choose.
The idea that using a wider range than necessary adds a small amount of error.
Right. So here's the question. If engineers or plant managers are often prioritizing inventory convenience or flexibility by selecting sensors with wide potential ranges and then operating them at high turndown ratios, maybe 10.1, 15.1, 20.1, effectively accepting that slight degradation in accuracy, that extra 0.05% or whatever it might be. What level of granular process optimization, what potential savings in energy, raw materials, or maybe improved reaction yield is still being left on the table in industrial facilities all over the world simply because critical sensors are running slightly outside their absolute optimum narrowest possible accuracy band due to these configuration choices? Are we chasing flexibility at the cost of ultimate performance?